Hello students, welcome to aptdemy. Myself Dr. Nandita, and today we will learn about a chapter of chemistry which is thermochemistry. Now let's see what we will have in this chapter. So first of all we will learn about the nature of chemical energy. Then we will learn about the first law of thermodynamics where we will learn about system and surroundings, internal energy, relating delta E to heat and work, endothermic and exothermic processes and state functions. Next topic would be on enthalpy. There we will learn about pressure, volume, work, enthalpy change, and then we will learn about enthalpies of reaction. Then the next topic would be calorimetry, where we will study heat capacity and specific heat, constant pressure calorimetry and constant volume calorimetry, which is also known as bomb calorimetry. And next topic would be on Hess's law. Then we will learn about enthalpies of formation, where standard free energy of formation will be studied. And then the next topic would be free energy and temperature. Then we will learn about free energy and the equilibrium constant, where we will be studying calculating enthalpies of reaction using enthalpies of formation. The next topic would be on bond enthalpies, where bond enthalpies and the enthalpies of reactions will be studied. And the final topic of this chapter would be on foods and fuels, where we will learn about foods, fuels and other energy sources. These are the list of references where from you can get even better ideas on the topics and subtopics that will be covered in this chapter, and also you will be able to solve some mathematical problems on the topics and subtopics that we are going to learn on this chapter. Okay, so in this chapter basically we will explore energy and its changes, and will understand the energy changes which is associated with chemical reactions. The study of energy and its transformations is actually known as thermodynamics, okay? And this area of study previously began in order to develop the relationships among heat, work and fuels in steam engines, okay? So the relationships between chemical reactions and energy changes will be examined that will involve heat. And that's why this portion of thermodynamics is called thermochemistry. That is the focus of this chapter. Now let's learn about the nature of energy. Energy is the capacity to do work or transfer heat, which requires to understand the concepts of work and heat. So concepts of work and heat need to be known, okay? So what is work? Work is the energy which is used to cause an object to move against a force. And on the other hand, heat is the energy which is used to cause the temperature of an object to increase. So when you apply heat on a substance, the temperature of the substance will increase. That is the concept of heat. So the ways in which matter can possess energy and how that energy can be transferred from one piece of matter to another, we need to know the fact. So let's talk about kinetic energy and potential energy. Any object, it can be either baseballs or can be even smaller like atoms or molecules. Any object possesses kinetic energy, and this is the energy due to the motion. So the magnitude of the kinetic energy, which can be denoted as Ek of an object, depends on its mass m and speed v, and can be represented as Ek is equal to half mv square. So kinetic energy, from this expression you can see that kinetic energy of an object increases as its speed increases. For example, if a car is moving at 55 miles per hour, that is mph, must have greater kinetic energy than if it is moving with 25 mph. Yeah. Now for a given speed, the kinetic energy increases with increasing mass, as can be explained from this equation. So a large truck which is traveling at 55 mph must have greater kinetic energy than a small sedan which is traveling at a same speed. Why? Because the truck has the greater mass than the small sedan. Okay. Now, being chemist, we are interested with atoms and molecules. So in chemistry, kinetic energy of atoms and molecules is of interest for chemists. So although these atoms or molecules are too small to be seen, instead of the fact these particles have mass and they are in motion, and hence they also possess kinetic energy. Now let's learn about potential energy. An object has potential energy because of its position which is relative to other objects. And basically the potential energy is the stored energy that arises from the attractions and repulsions that an object experiences in relation to other objects. For example, the energy stored in a stretched spring, in a weight held above your head, or in a chemical bond, etc. Now let's consider this scenario. Here a cyclist is on the top or is still and there is no motion. So what can we say? That there is high potential energy here, but as the cyclist is not cycling, so the kinetic energy is 0 in this case. Whereas while the cyclist is moving down, the potential energy is getting decreased and the kinetic energy is increasing. So due to the attractive force of gravity, the potential energy of the cyclist and her bicycle is greater at the top of the hill, that is considered here, than at the bottom, that is here. So the bicycle easily can move down the hill with increasing speed. Okay. So as a consequence, the potential energy initially stored in it is getting converted into its kinetic energy. So the potential energy will decrease as the bicycle will roll down the hill, but what will happen to the kinetic energy? The kinetic energy will increase as the speed is increasing. Okay. And such interconversion of energy, that is high potential energy from here to the high kinetic energy here, that is the such interconversion of energy with one form decreasing while the other form increases, is the basis of thermodynamics. Okay, that you need to remember. So what will happen for atoms and molecules? So gravitational forces play a very negligible role in the ways atoms and molecules interact with one another because they are very small. So forces that arise from electrical charges are more important when we are dealing with atoms and molecules. So important form of potential energy in chemistry is electrostatic potential energy, which is denoted as EEL, and this is arising from the interaction between charged particles. And this energy is proportional to the electrical charges on the two interacting objects Q1 and Q2 and inversely proportional to the distance d among the Q1 and between the Q1 and Q2. So EEL can be written in this way, is equal to K, EEL is equal to K multiplied by Q1 Q2 divided by D. Here in this equation K is a constant of proportionality and the value of K is 8.99 times 10 to the power 9 joule meter per coulomb square, and this C is the coulomb, which is a unit of electrical charge, and J is the joule, which is a unit of energy, and at the molecular level the electrical charges Q1 and Q2 are typically on the order of magnitude of the charge of the electron, which is 1.6 times 10 to the power minus 19 coulomb. Okay. So the above equation actually shows that the electrostatic potential energy is going to 0 as d becomes infinite, because d is coming in the denominator of this equation. So the 0 of electrostatic potential energy can be defined as infinite separation of the charged particles. Now, if you consider this scenario, you can see here that when Q1 and Q2 have the same sign, for example, if both of them are positive, the two charged particles will repel each other. You can consider this Q1 and Q2, they are of similar sign, maybe they are positive, and so when they are getting away from each other because of the similar charge, what will happen? In this case, EEL must be positive and the potential energy will decrease as the particles are moving farther and farther apart from each other. Okay. Now let's consider the other scenario where Q1 and Q2 have opposite signs, as can be denoted here with two different colors. So what will happen? Because of the fact that they are opposite in sign, the particles will attract each other and an attractive force will pull them toward each other. So in this case, EEL must be negative and the potential energy will increase or becomes less negative as the particles are moving apart, as can be seen here. As the particles are moving farther apart, their electrostatic potential energy should approach to the value of 0. Okay. So the relationship between the energy changes as seen in the macroscopic world to the kinetic or potential energy of the substances at the molecular level, we need to know the fact. Many substances, for example fuels, they will release chemical energy when they react. We know that. So energy due to the potential energy which is stored in the arrangements of their atoms, as we have learned few slides back. And the energy a substance possesses because of its temperature, that is due to the thermal energy, is associated with the kinetic energy of the molecules in the substance. Now let's learn about the units of energy. So the SI unit for energy is the joule, and this can be pronounced as JOOL, joule. Yeah, and this is by the name of a famous British scientist, James Joule, who investigated work and heat. And 1 joule can be represented as equal to 1 kilogram meter square per second square. So mass of 2 kg moving at a speed of 1 meter per second hence possesses a kinetic energy of 1 joule. This is by definition. So for Ek, as you have learned that Ek is equal to half mv square, if you put the value of the mass, that is 2 kg here, and also the velocity, that is 1 meter per second square here, you will get Ek as 1 kg meter square per second square, and that is the definition of 1 joule. Okay. As a joule is not a large amount of energy, it is very small. So we will consider kilojoules while discussing the energies which is associated with any chemical reaction. Okay. Energy changes that is accompanying any chemical reaction have been expressed in another unit which is known as calories, and this is a non-SI unit. Okay. So how can we define calorie? A calorie, which is also be written as small cal, cal, it was previously defined as the amount of energy that is required to raise the temperature of 1 gram of water from 14.5 degrees C to 15.5 degrees C. This was the previous definition of calorie. But now calorie is defined in terms of the joule, that is our SI unit. Okay, so you have to keep the number in mind that 1 calorie is equal to 4.184 joule exactly. Okay. So we have another unit that is known as nutritional calorie, and this is actually used while studying in nutrition related topics. Okay, so related energy unit used in nutrition is the nutritional calorie, which is denoted as capital C, and 1 cal here is equal to 1000 cal. Here you just check the capital C here, and here is our small c, and this is equal to 1 kilocalorie, kcal. Now let's learn about system and surroundings. Okay. So a limited and well-defined part of the universe is the focus while analyzing energy changes. Anything in the universe can be system, okay, and rest of just accept the system what we are considering, except the system, everything else in the universe are known as surroundings. Okay. So the portion we actually single out for study is called the system, and everything else is called the surroundings. Now let's take an example. When we study the energy change of a chemical reaction, very common, the reactants and products are actually constituting the system. So in a chemical reaction, reactants and the products are considered to be the system. And what would be the surroundings then? The container and everything beyond it are considered the surrounding. Okay. Now let's classify our systems. The systems can be open system, closed system, or isolated. How can we define them? Let's talk about open system. An open system is one in which matter and energy both can be exchanged with surroundings. For example, an uncovered pot of boiling water on a stove can be considered as open system. Heat comes into the system from the stove and water is released to the surroundings in form of steam. Now what is closed system? Actually in this chapter of thermochemistry we will mostly talk about closed system. So for closed system, these are the systems that can exchange energy but not matter with the surroundings. Okay. So closed system can only exchange energy but no matter with the surroundings. For example, a mixture of hydrogen gas H2 and oxygen gas O2 in a cylinder fitted with a piston, as can be represented by this schematic. Okay. So this is a representation of a closed system. Here the system is just the hydrogen and oxygen, and the cylinder, piston and everything beyond them, including us, are the surroundings. If the gases react to form water, energy is also liberated in this reaction, and the reaction can be represented in the following manner, that is 2H2 gas plus O2 gas giving rise to 2 moles of water in steam form and also releasing some energy. Okay. Although the chemical form of the hydrogen and oxygen atoms in the system is changed by its reaction, the system has not lost or gained any mass. This means that it has not exchanged any matter with the surrounding. However, it can exchange energy with its surroundings in the form of work and heat. That you also have to keep in mind. Although no mass is exchanged between system and surrounding, yet some energy can be either released or generated in such kind of systems in form of work or heat. Okay. Now what is isolated system? An isolated system is one in which neither energy nor matter can be exchanged with the surroundings. No matter and no energy are getting transferred between systems and surroundings. So this is called isolated system. For example, an insulated thermos which is containing hot coffee actually is an example of isolated system. However, we know that the coffee eventually cools down with time, so it is not perfectly isolated, but to some extent it is an example of isolated system. Okay, now let's learn about transferring energy and work and heat. Okay, so from the previous discussion we can say that in two ways energy can be exchanged or expressed in our everyday life, in form of work or in the form of heat. So work is done, for example, if you consider the right hand side picture, for example this one, you can understand that work is done as energy is transferred from the pitcher's arm to the ball, which is directing it toward the plate at high speed. Okay, and energy is transferred in the form of heat, causing the motion of an object against force and causing a temperature change are the two general ways that energy can be transferred into or out of the system. We are also talking about this scenario where heat added by burner to water and makes water temperature to rise. So a force is any push or pull exerted on an object. So we define work as denoted as W as the energy transferred when a force moves an object. Okay. The magnitude of this work must be equal the product of the force F and the distance D. The force you are applying and the distance the object is moving by applying the force. So, to move the object, so what can be defined as W is equal to F times D. Okay. Now, work is performed when we lift an object, for example, this one or maybe any heavy object against the force of gravity. Now, if we define the object as the system, then we, as a part of the surroundings, are performing work on the system and transferring energy to it. The other way in which energy can be transferred is as heat. Okay, heat is the energy which is getting transferred from a hotter object to a colder one. For example, if we consider a combustion reaction, for example, as the burning of natural gas which releases the chemical energy which is stored in the molecules of the fuel. So this is the example of energy transfer in form of heat. Okay. Now, if the substances involved in the reaction are defined as the system and everything else as the surroundings, then the released energy causes the temperature of the system to increase. Okay. Energy in the form of heat is then transferred from the hotter system to the colder surroundings. So that's how heat is getting transferred from a hotter object to a colder object by means of energy in the form of heat. So with this idea, let's solve illustration 1, which is actually based on the idea on calculation of energy changes. So illustration 1 is asking or saying that a bowler lifts a 5.4 kg or 12-pound bowling ball from ground level to a height of 1.6 meter, which is 5.2 feet, and then drops it. Now question A is asking what happens to the potential energy of the ball as it is raised. B is asking what quantity of work in joule is used to raise the ball, and C is asking after the ball is dropped it gains kinetic energy. If all the work done in part B has been converted to kinetic energy by the time the ball strikes the ground, what is the ball speed just before it hits the ground? And there is a note that the force due to gravity is F is equal to m into g, where m is the mass of the object and g is the gravitational constant, which is 9.8 meter per second square. Okay, let's try to solve the problem. Now first we have to write down the formula for work. We know that W is equal to, as we have learned just in the previous slide, that W is equal to force times distance. Okay. And another fact is that the kinetic energy of the ball just before it hits the ground is its initial potential energy. That you have to keep in mind. Okay. And now we will solve for A. Okay. So because the ball is raised above the ground, as the ball is raised above the ground, its potential energy relative to the ground should increase. What will happen to the potential energy? Its potential energy relative to the ground should increase. This is the answer of problem A. Okay. Now let's solve for B. So the ball has a mass of 5.4 kg. It is given our M. Okay. And it is lifted 1.6 meter here. To calculate the work performed to raise the ball, we can use the equation as given here. That is W is equal to F times D. Okay. So let's write it again. Okay. Now in place of F, that is force, it can also be written as mg and D. Instead of, in place of F, we can write mg. Yeah, as given here. Okay. So now we all the values we have. So let's just put the values and calculate it. Okay. So for M we have 5.4 kg. Okay. And for M it is given, the G is given as 9.8 meter per second square, and the distance is, that is how much it is lifted upward, is 1.6 meter is also given. Okay. Now if you calculate, you will get 85 kilogram meter square per second square, and this is nothing but our 85 joule. Okay. So the bowler has done 85 joule to work to lift the ball to a height of 1.6 meter. So the work done by the bowler is 85 joule to lift the ball up to this distance, 1.6 meter. Okay, I hope you have understood. This is the answer of B. Now you keep this in mind. So we don't have space here to solve the C, problem C. So we will solve the problem C in the next page. Okay. Let's go to the next slide. Now for C, when the ball is dropped, its potential energy is converted to kinetic energy. When dropped, this is the solve for C. When the ball is dropped, its potential energy is converted to kinetic energy. Okay. And the kinetic energy before touching the ground, we have calculated it. This is nothing but the initial potential energy, as I have talked about it in the beginning. So this should be before touching the kinetic energy. The kinetic energy must be the initial potential energy, that is our 85 joule, as we have calculated in the previous slide. Okay, so we can write, as we have learned it, EK, expression of EK as half mv square is equal to 85 joule or 85 kilogram meter square per second square. Okay, that we can write. This is the definition of joule. The same. Now we can solve for V from this equation. Now let's solve for V. So from this equation we can write V square as 2 EK divided by M. Let's put the values. 2 times 85 kilogram meter square per second square divided by 5.4 kg as our mass. It was given. So now if you calculate, you will get for V square as 31.5 meter square per second square, and this is for V square. Okay, now if you calculate for V, it should be root over 31.5 meter square per second square. So if you calculate, you will get 5.6 meter per second. So this is the number for V that has been asked in the problem number C. I hope you have understood. Now let's move on to the next slide. Here we will learn about the first law of thermodynamics. So let's just talk a bit before we are going into it. So what we have learned, that potential energy of a system can be converted into kinetic energy and vice versa. That is interconversion of energy. This concept we have learned already. Now energy can be transferred back and forth between a system and its surroundings in the forms of work and heat. That we also have learned. Now all the conversions and transfer actually leading to most important observation in chemistry, What is that? Energy can be neither created or nor can be destroyed. Any energy that is lost by a system must be gained by the surroundings and vice versa. And this important observation, that is energy is conserved, is known as the first law of thermodynamics. This is the first law of thermodynamics, that energy cannot be created or destroyed. It can only be transferred, but energy of universe must be conserved. Okay, this is the first law of thermodynamics. Now with this idea, let's learn about internal energy. So the first law of thermodynamics can be used to analyze energy changes in chemical systems. So all the sources of kinetic and potential energy in the system must be considered. The internal energy, which is denoted as E of a system, can be defined as the sum of all the kinetic and potential energies of the components of a system. Now, if you consider a closed system, the internal energy should include not only the motions and interactions of the H2 and O2 molecules, as we have talked about this equation before, but also the motion and interactions of the nuclei and electrons as well. So the numerical value of the system's internal energy is actually practically not known. Okay. So what we will consider? In thermodynamics, the change in internal energy is of concern, and this is accompanies a change in the system. Now, if you consider a system with an internal energy, initial internal energy of E initial, and this is undergoing a change, and this might involve work being done or heat being transferred. These are the two possibilities. So after the change will occur, the final internal energy of the system can be denoted as E final. So the change in the internal energy, that is delta E, can be defined as the difference between E final and E initial. So the change in internal energy, that is delta E, can be written as E final minus E initial. Okay. Although the actual values of E final or E initial for any system can't be determined, as we have discussed, however, we need only the value of delta E in order to apply the first law of thermodynamics. So thermodynamic quantities actually is having three parts: a number, a unit, which together give us the magnitude of the change, and a sign that gives the direction of the reaction. Okay. So now let's talk about the sign. Okay. A positive value of delta E can be resulted only if E final is greater than E initial. From this equation, you can comment. Okay. And this is indicating that the system has gained energy from its surroundings, because the final energy is greater than the initial energy, internal energy. So the system is gaining energy from its surrounding. But a negative value of delta E can be resulted when E final is less than E initial. This is indicating that the system has lost energy to the surrounding, because the final energy is much lesser than the initial energy. And you can also see the schematic to actually learn or actually have the better concept on this. And you can see that here, this is the initial energy of the system, initial state of a system, and defined as E initial, and loss of energy from the system can be represented by the blue arrow, that is energy from this internal energy plot. You can see that the loss of energy, that is energy is going down, can be represented as the blue arrow and pointing downwards from the initial state to the final state. This is the initial one, this is the final one, the final state is having less energy than the initial state. Whereas in this case, if you consider this is an initial and the red arrow is pointing towards the higher value of energy, and so there is gain of energy by the system, which is represented by the red arrow, which is pointing upward from the initial state to the final state. Okay, that we have talked about here. So in order for any energy changes, only system is considered here. Okay. Any increase in the energy of the system must be accompanied by a decrease in the energy of the surroundings and vice versa. If there is increase in surroundings energy, system's energy must go down. Okay. So in a chemical reaction, the initial state of the system is actually referring to the reactants and the final state is referring to the products. So in this reaction, as we have talked about this reaction before, 2H2 gas plus O2 is giving rise to 2H2 liquid. What is the initial state? This is the initial state, that is 2H2 gas plus O2 gas, and the final state is the 2H2O liquid. Okay. Now when hydrogen and oxygen form water at a given temperature, that is the product, the system will lose energy to the surroundings. Because energy is lost from the system, the internal energy of the products, that is the final state, must be less than that of the reactants, that is the initial state. And hence, the delta E for the process must be negative, as E product or E final is less than the E initial for this reaction. So the energy diagram as represented in this schematic is also showing that the internal energy of the mixture of H2 and O2, that is the reactant, is greater than that of the H2O, which is produced in the reaction, that is the product of the reaction. You can also see the fact from this energy diagram, that is here delta E is less than 0. The energy of the product is less than the internal energy of the reactants. Okay. Now we will relate delta E to heat and work. How? If internal energy is considered as the system's bank account of energy, okay, deposits or withdrawals can be made as we do in the banks in increments of heat or in increments of work. So deposits is considered as increments of heat and withdrawals is considered as increments of work. Okay. So deposits actually increases the energy of the system and leading to a positive delta E value, whereas withdrawals decrease the energy of the system and giving rise to negative value of delta E. Now when a system is undergoing any chemical or physical changes, the change in internal energy, that is delta E, must be the sum of the heat added to or liberated from the system, Q, and the work done on or by the system, W, can be written as delta E is equal to Q plus W. It is not seen here, maybe I can write it down. So delta E must be equal to Q plus W. Okay. So this is the equation you have to keep in mind. Now let's move on. Now when heat is added to a system or what is done on a system, its internal energy should increase. So when heat is transferred to the system from the surrounding, Q must have a positive value. So we can consider this schematic. Now if you add heat to the system, is like making a deposit to the energy account. The energy of the system should increase. Okay. So work done on the system, you are depositing in the bank of internal energy, that is represented here. Okay. So heat is work done on the system or heat gained by the system So Q has a positive value in this case. Now adding heat to the system is like making a deposit to the energy account, the energy of the system thus should increase, as we have talked about before. Now when work is done on the system by the surroundings, W has a positive value, okay, according to this schematic. Now we are talking so far about this one. Now let's talk about here. This is in contrary with this left hand scenario. What is happening here? Both the heat lost by the system to the surroundings and the work done by the system on the surroundings. Okay, heat lost, heat is going out from the system. The system is losing energy, and work is also done by the system to the surrounding. Okay, so both the heat lost by the system to the surroundings and the work done by the system on the surroundings have negative values here. Q is less than 0 and W is less than 0, negative values. So that is, they lower the internal energy of the system, as they all are directing towards outside. System is not getting anything but releasing. So internal energy is getting down. Now they are actually considered as the energy withdrawals and lower the amount of energy in the system's account. Okay. Now any energy entering the system as either heat or work should carry a positive sign that we have considered in the left hand schematic, and here it should carry a negative sign. Okay. Now let's learn from this table about the sign conversion for Q, W and delta E. For Q value is positive. It means that the system is gaining heat. But if it is negative, it means that system is losing heat. For W, if it is positive, it means work is done on the system. But if it is negative, it means that work is done by the system to the surrounding. Okay. For delta E, if it is positive, it means that net gain of energy by the system. But if it is negative, it means that loss of energy by the system. Okay, or release of energy from the system to the surrounding. Now, with this idea, let's solve illustration 2, which is based on the idea to relate heat and work to changes of internal energy. Illustration 2 is saying gases A and B are confined in a cylinder and piston arrangement like here, that is given in the figure, and react to form a solid product CS, and the reaction can be represented as A gas plus B gas is giving rise to C solid. As the reaction occurs, the system loses 1150 joule of heat to the surroundings. The system is releasing heat. The piston moves downward as the gases react to form a solid. As the volume of the gas decreases under the constant pressure of atmosphere, the surroundings do 480 joule of work. Okay, so here actually we are given the loss of heat and also the work done on the system is given. Now they are asking what is the change in the internal energy of the system. Now let's try to solve it. Now as heat is transferred from the system to the surrounding, heat transfer from the system to surrounding as energy is released, okay, and work is done on the system by the surroundings, work is done by the surrounding on the system. So what will be for Q? Q must be negative in sign and W must be positive. Okay. So for as Q is given here, this is our Q and this is our W. So we will just decide the sign of Q and W and put the values to calculate the delta E. Okay. So what we can write for Q, we can write minus, because it is negative, so it will be having minus 1150 joule. And what will be for W? W is positive, so it should be 480 of joule. Now from first law, the concept of internal energy. So what we have learned as the formula of delta E, and delta E can be written as Q plus W. Okay, so our Q value is minus 1150 joule and our W is 4. Our W is 480 joule. Now if you calculate, you will get minus 670 joule as our delta E. So delta E is equal to minus 670 joule. This is what they have asked to calculate. So the negative sign for delta E, as you can see here, this actually the negative sign of delta E actually indicates, let's box it, what it indicates. The net quantity of 670 joule is energy has been transferred from the system to surrounding. Okay, so the 670 joule of energy is transferred from system to surrounding. So system is losing the energy and giving off the energy to the surrounding. Is transferred from system to surrounding. Okay, the negative sign is indicating the fact. Okay, so very simple. I hope you have understood. Now let's move on. Now let's talk about the endothermic and exothermic processes. Okay, what are they? As heat transfer to and from the system is the central topic of the discussion in this chapter, some special terminology will be used to indicate the direction of heat transfer. Direction means either it is transferring from system to surrounding or surrounding to system. How? When a process occurs in which the system absorbs heat, that is, system's energy is getting increased, the process is actually called endothermic. What does endo means? Endo means into, that is, heat is getting transferred into the system, and this kind of process is called endothermic process, as can be considered in this reaction. So here our system is reactants and products that is kept inside the beaker, and the surroundings are the solvent which is kept at initially at room temperature, and everything else is also surrounding. Now what is happening here, you can also check the temperature change here. Heat is flowing from surroundings into the system. So system is gaining energy, and this is actually referring to as endothermic process, where the temperature of surroundings is dropping, as you can see from the thermometer data. This is also well below the room temperature. Okay, so the system is gaining energy and the surrounding is losing energy in terms of heat. So this kind of processes are called endothermic process. So during an endothermic process, for example, melting of ice, heat flows into the system from its surroundings, as we have just a while ago we have discussed. Now if we that as part of the surroundings will touch the container in which ice is melting, what will happen? We will feel that the container is very cold. So the container feels cold to us, as what is happening here? The heat is passing from our hand to the container. That is, we are the part of the surroundings. So from surroundings to the system, that is the container which is containing the molten ice water is considered as the system. So from our hand, that is the surroundings, energy in form of heat is getting transferred to the container. Okay, so the system is gaining energy from its surrounding. So this type of processes are called endothermic processes. Now let's learn about the exothermic one. This is just opposite. Now you can consider here this scenario. Here also the system is reactants and the surrounding is considered as the air around the reactants. Okay. Now heat is flowing violently, as you can see here, from system into the surrounding. If it is considered as your system, heat is getting transferred to the surrounding from the system. Okay, and the surroundings temperature is getting increased. So such kind of process in which the system loses heat is called exothermic process. And what does exo means? Exo means out of. That is, heat is getting out of the system and the surrounding is gaining energy. So for example, any kind of combustion reaction, for example combustion of gasoline, heat exists or flows out of the system into the surroundings. Now let's learn about state functions. What are the state functions? So as we have learned before that there is no way to know the precise value of the internal energy of the system, E. So it does have a fixed value for a given set of conditions. What are the conditions? So we actually are talking about the change in internal energy of any system, that is delta E, but it is not possible to learn or to know the exact value of internal energy for any system. So we need to focus on some parameters or set of conditions. What are they? These conditions that influence internal energy should include the temperature and pressure. Now internal energy of a system must be proportional to the total quantity of matter in the system, because energy is an extensive property. Now if we consider this scenario here, our system is 50 gram of water at 25 degree centigrade, and it could reach to this state by 2 steps. What are the steps? It can reach to this position or this state by cooling 50 gram of water from 100 degree centigrade to 25 degree centigrade, that is indicated, that is here, to 25 degree centigrade, or by melting 50 gram of ice and subsequently warming the water to 25 degree centigrade. So there are 2 ways. In this case, this is our system. So initially hot water cools to water at 25 degree centigrade. Once this temperature is reached, system has internal energy of E. So 50 gram of water from 100 degree centigrade, it can be cooled down to go to this position or the state of 50 gram of water at 25 degrees centigrade, Or another step could be that 50 gram of water in 0 degree centigrade, it should be warm up at 25 degrees centigrade when this temperature is reached, and again this is a system's internal energy E is the same. Okay, so this actually lead us to conclude that the internal energy of the system is fixed and it is not dependent how the system is reaching in this state. So, internal energy E is a state function. Any state function which depends only on the present state of the system and not on the path which has been taken to reach the system in this state is known as state function. So, we have learned that internal energy is a state function and depends only on the initial and final states of a system and not on how the change occurs. So, we can reach the same, or we can reach the system by several other ways, but the internal energy associated with any of these changes must be same. So, internal energy is dependent only on the state but not the path is taken to reach the state. Okay. For example, suppose you drive from Chicago, which is 596 feet above the sea level, to Denver, which is 5280 feet above the sea level. No matter which route you are taking, the altitude change is same, that is 4684 feet, and the distance you travel depends on the route. So, there is analogy between altitude in this example to a state function because the change in altitude is independent of the path that has been taken. Okay. Now, the distance which is traveled is not a state function. This is different for different path has been taken. Some thermodynamic quantities, if you take example, for example, E, are state functions as we have discussed while ago. So, other quantities, for example, Q and W, the specific amounts of heat and work produced which depend on the way in which the change occurs. Nonetheless, if changing the path by which a system goes from initial state to a final state should increase the value of Q, that path change will also decrease the value of W by exactly the same amount. So, the result is same for these two paths in this case. Now, let us consider the discharging process of a flashlight, battery of a flashlight. Yeah. So, as can be represented here. So, its internal energy for this process should decrease as the energy stored in the battery is released to the surroundings. Okay. But we will consider two possible ways of discharging the battery at constant temperature. The first one is if a wire shorts out the battery, no work is done. We are considering this scenario. As nothing is moved here against a force. So, all the energy is actually losing from the battery is in the form of heat. The wire gets warmer in this case and releases heat to the surroundings. Okay, this is path number 1. Okay. What is another path? If the battery is used to make a motor turn, that is here, the discharge produces work in this case. Yeah. But here some heat is released, but this is not as much as we have considered in this case, in the first case. So, magnitudes of both Q and W are different in these two cases. If the initial and final states of the battery are identical in the two cases as we have discussed here, so delta E, that is Q plus W, must be the same in both cases, as delta E is a state function. We have learned it. Okay. So, we know that as we have discussed in the previous slide, that delta E actually depends only on the initial and final states of the system, but not on the specific path taken from the initial to the final state.